Good morning. My name is Kumar, assistant professor in Department of Mathematics at Aditya Nandaya University. I teach theoretical computer science for M.Sc mathematics course, and the textbook for this paper is Theory of Computer Science, written by Mishra and Chandrasekhar. And theoretical computer science is a part of general computer science and mathematics that explains on more mathematical topics of computing, including the theory of computation. By using the concepts of theoretical computer science, we can learn or we can observe how the computer system has been working behind the screen. Similarly, how the machine tools has been working. And theoretical computer science covers so much of topics. But I mentioned only few of them here. Algorithms, data structures, automated theory, cryptography, and computational geometry, and so many. But in the present semester, we learn only automated theory and the context-free grammar and the regular sets and so on. And coming to the syllabus, in this paper, we learn 4 units. First unit is the theory of automata. Second unit is formal languages. Third unit is regular sets and regular grammars. Fourth unit is Turing machines. The applications of the theory of automata and formal languages in constructing the algorithms for the computer languages, and the context-free grammar, which is the subtopic of Unit 3, the application of context-free grammar in all artificial intelligence, and similarly the application of Turing machine in the machine learning. And we start Unit 1. Unit 1 in the first definition is automaton. Automaton. Without the direct participation of a man, the system can be transformed or transmitted energy, materials, and information for performing some functions is known as automaton. So, without the direct participation, the system can be transformed or transmitted energy, materials, and information for performing some functions is known as automaton. And the examples are automatic machine tools and automatic packing machines and automatic photo printing machines. And this is the block diagram of an automaton. Here I1, I2, IP are inputs, O1, O2, OQ are outputs. The machine has been working in the form of states, namely Q1, Q2, and so on, Qn. Here I want to say a basic example of automaton. In our childhood, we have seen the weighing machines at the railway stations or at the bus stations. At the weighing machines, we put 1 rupee or 2 rupee as an input to the machine. The machine gives a weighing printed record as an output. Meanwhile, the machine has been working in the form of states Q1, Q2, and so on Q1. This is the basic example and basic application of an automaton. In computer science, automaton means discrete automaton. And there are 5 characteristics of automaton. First one, input, output, state relation, and output relation. In the block diagram, we have seen input, output, and states. So, input, it is denoted by I1, I2, IP at the discrete times E1, E2, and En. The set of all inputs or the collection of all inputs is called the input alphabet, denoted by sigma. So the input alphabet is the set of all inputs. And the second one is output. It is denoted by rho1, rho2, rho2. And states denoted by Q1, Q2, Qn at any instant of time. And the fourth one is state relation. The next state of an automaton is determined by the present state and the present input. Simply, the relationship between the two states is known as state relation, and fifth one, output relation. It is related to either the states only or both the input and the state. And there are four types of an automaton. First one is an automaton without a memory. Second one, an automaton with a finite memory. Third one, more mission. And fourth one, melee mission. Coming to the first one, when the output depends only on the input, then it is called as an automaton without a memory. When the output depends on the states as well, then it is called an automaton with a finite memory. Whereas the output depends only on the states, it is known as more mission. Whereas the output depends both the states as well as the inputs is known as melee mission. Mission strings. A string is a finite sequence of symbols from sigma. We have already learned sigma means the set of input symbols. So a finite sequence of input symbols is also known as string. So it is denoted by X, Y, Z, W, 0 and 1 and capital lambda. Capital lambda means empty string. And some more strings are 0, 1, 1, 0, 1 or 1, 0, 1 or 0, 0, 1 and some more examples X, Y, X, Y, Z, Z. These are the some more examples of strings. And some notations. Sigma star denotes the set of all strings including the empty string, whereas sigma plus is the set of non-empty strings. That is, sigma plus is equals to sigma star minus single non-empty string. And next definition, finite automaton. A finite automaton can be represented by 5 tuples, namely Q, sigma, delta, Q naught and capital F, where Q is the set of states, sigma, the input alphabet, is the set of inputs, where delta is mapping from Q cross sigma to Q. The function it is known as transition function. So it is function which describes the change of states during the transition. So generally the transition function represented by a transition table or by a transition diagram. Fourth one, Q naught, which belongs to capital Q, is the initial state, and fifth one, capital F, is the set of final states. Next definition, transition system or a transition graph. A transition graph or a transition system is a graph in which each matrix represents a state and each edge represents a transition of a state and edge with a label input and output. Here Q naught, Q1 are states and this is the edge. 0 by 0 represents input and output, 1 by 0 represents input and output, and 1 by 1 represents input and output. And the definition of a transition system. It is also a 5-tuple Q, sigma, delta, Q naught, and capital F, where Q, sigma, capital F are same as of finite automaton. So Q is set of states, sigma is the input alphabet, capital F is the set of finite state, which is same as in the definition of finite automaton. And the fourth one, Q naught, which is subset of capital Q, which is also a non-empty. And then I get a finite subset of Q cross sigma star cross Q, where sigma star is the set of all strings. Difference between finite automaton and transition system. Finite automaton contains only one initial state, whereas transition system contains more than one initial state. So when we compare the 5 tuples of both, fourth one in finite automaton is just a Q0, which is the initial state, whereas in the transition system, fourth coordinate is capital Q0. So from this, we observe that every finite automaton can be a transition system, but a transition system need not be a finite automaton. Now, we see some notations in transition graph. Here, Q0, which is in the circle, indicates state. Circle with the arrow mark indicates initial state. Concentric circle indicates final state. And the curved edge indicates edge. I by what indicates input and output. And this is the graph. Okay. Here, Q0 and Q1 are states. Q0 and Q1 are states. And Q0, which is in the circle along with the arrow mark, indicates initial state. So Q0 is initial state. Q1, which is in concentric circle, means final state. And this is one edge, another edge, third edge, fourth edge. Here, 0 by 0 means 0 is both input and output. 1 by 0 means 1 is input and 0 is output. So, if the system is in the state Q0 and input 1 is applied, then the system moves to Q1. So it is directed energy from Q0 to Q1. So Q0 to Q1. If the system is in the state Q0 and the input 0 is applied, then the system remains at the same state Q0. So with the label 0 by 0. Suppose if the system is in the state Q1 and applied and input 0 is applied, input 0 is applied, then the system moves to Q1 to Q0. Q0 to Q0. And this is another graph. Here there are 4 states, Q0, Q1, Q2 and Q3. So these are the states, Q0, Q1, Q2, Q3 are states. And Q0, which is in the circle along with the arrow mark, is initial state, and Q1, which is also in circle along with the arrow mark, indicates initial state. So Q0 and Q1 are initial states. Q3 is, which is in the concentric circle. So Q3 is final state. Q3 is final state. So this is one edge, this is another edge, this is an edge, and these are the edges. Here 1 0 1 1 is input, 0 is output. In capital lambda, which is the empty string, so this is the input and 0 is output. 0 is output. Come back to the finite automaton definition. Finite automaton can be represented by 5 tuple Q, sigma, delta, Q naught, and capital F, where capital Q is set of states, sigma is set of inputs, delta is the transition function, Q naught is the initial state, and capital F is final state. Consider this graph. Here the states are Q0 and Q1. So Q is equal to set of states Q0 and Q1. And the inputs are 0 and 1. So sigma is the set of 0 and 1. And the Q1 is final state. So capital F is equals to Q1. And Q0 is the initial state. Q0 is the initial state. What is delta? Delta is a function from Q cross sigma to capital Q. So that means delta of Q, which is Q0 and sigma 0. So when the system is at Q0 and input 0 is applied, then the system moves to Q0. Similarly, delta of when the system is at Q0 and the input 1 is applied, then the system moves to Q1. So here Q0 belongs to capital Q, 0 belongs to sigma, and Q0 belongs to capital Q. So now delta of Q1 and 0. So when the system at Q0, Q1 and 0 is applied, then system moves to Q0. Similarly, delta of Q1 1 to Q1. So this is the finite automaton, and this is the example of finite automaton. The transition system is again 5 tuple Q, sigma, delta, Q0 and capital F. We have explained the difference between the finite automaton and transition system. In finite automaton, it contains only one initial state, whereas a transition system contains more than one initial state. Here, Q0 and Q1 are initial states, so this is one of the examples for the transition system. Now we see the definition. The transition system accepts a string W in sigma star if it satisfies the following two properties. First one, there exists a path which starts from some initial state and travels along the arrows and stops at some final state. And second property, the path value obtained by concatenation of all edges of the path, which is equals to the string W. And we see the example. Consider the transition system determined the following four. First one, the initial state, the final state, the acceptable of the string 1 0 1 0 1 1 and the acceptable of the string 1 1 1 0 1 0. So solution, coming to the solution. So first one, the initial stage. The initial states are Q0, Q1. And second one, the final state is Q3. Third one, acceptable of the string 1011. So consider the string one zero one zero one. So now the system set some initial state Q0, and input 1 is applied to the system, then the system remains at Q0. Now the input 0 is applied to the system, then the system moves to Q2. Now apply the string 1011, then the system moves to Q3, which is the final step. So come back to the definition. A transition system, first one, starts from initial and travels along the arrows and terminates at the final state Q3. And second one, the path value obtained by concatenation of NQ. So Q0, Q0, Q2, Q3 is the path of the string 101011. And fourth one, acceptability of the string acceptability of the string 101. So again consider the string now we start at some initial state Q0, and input 1 is applied to the system, then the system remains at Q0. Again, input 1 is applied to the system, and then system stays at Q0. Now, the input 1 is applied to the system, then it's also again at Q0. Now, the input 0 is applied, then the system moves to Q2. When input 1 is applied to the system, then the system remains at the same state Q2. When the 0 is applied, now we observe here from the graph, at Q2, there is no path to find the input 0. So, this is the path for 1, this is the path for the input 1011, and this is the path for the empty string. So there is no path for the input 0. So there is no path for the string 11101. There are two properties of a transition function. First property, that of q comma lambda is equals to q. This means that the state of the system can be changed by an input symbol only. And the second property, for all the strings w and input symbol a, that of Q comma AW is equals to Z of Q comma A comma W. And the second one, Z of Q comma WA is equals to Z of Q comma W comma A. So please note these two properties. We can use these properties in the next examples. And coming to the next example, prove that for any transition function delta and for any two inputs x and y, delta of q comma xy is equals to delta of q comma x comma y. So initially we can prove this by mathematical induction method. Mathematical induction on the length of what? That is mod what? Mod y indicates the length of what? So let the length of y is equals to what? So then consider y is equals to some which belongs to sigma. So another case of 1 is, or in another case of 1, then of q comma xy when y is equals to a. So q comma xy which is equals to then of q comma yeah, by property 2. By property. So assume that equation 1 holds for all the strings x and y with length of y is equals to yeah. Now we prove this by for the length n plus 1. So now consider length of y is equals to n plus 1. So consider y is equals to y1 yeah, where the length of y1 is equals to n. So the other case of 1 is delta of q of x y. So delta of q comma x when y is equals to y1 yeah, which is equals to delta of q comma x y1 comma a again by property 2. So similarly, del of q comma x comma y1 comma a. Again by property 2. Now consider R case of 1. What is R case of 1? Del of q comma x comma y1 yeah, which is equals to del of q comma x comma y1 yeah. So here LHS is equals to RHS. Therefore the equation 1 is true for all strings. For all strings. Equation 1 is true for all strings. So next example, prove that del of q comma x is equals to del of q comma y, then del of q comma x z is equals to del of q comma y Good. So solution. Consider del R Q gamma x is equals to del R Q gamma y. So now we do del R Q gamma x again, which is equals to del R Q gamma x gamma z by again property 2. So from 1 del R Q gamma x is equals to del R Q gamma y. So that remains del R Q gamma x replaced by del R Q gamma y gamma z. So now we take equation number 2. So del R Q gamma y z, and then we get del R Q gamma y gamma z. Again, del R Q gamma y replaced by del R Q gamma x. So equation 2 and 3 are same. So that implies therefore del R Q gamma x again is equals to del R Q gamma y z. Next definition, acceptability of a string by a finite automaton. A string x is accepted by a finite automaton whenever del R Q gamma Q naught gamma x is equals to Q, where for some Q belongs to capital F, where capital F is set of final states. Now we see there are some examples. Consider the finite state machine whose transition functions are given by the table. So when we observe this table, Q naught is the initial state as well as final state. So Q naught is both initial and final state. We find the sequence of states for the string 1 1 0 1 0 1. So for the solution, the transition functions that are of the string starts at the initial state Q naught and 1 0 1 0 1. Okay. When we give input 1 to the system at the Q naught, then it moves to Q1. So the rest of the string is 1 0 1 0 1. Now the input 1 is applied to the state Q1, then it moves to Q0. Then it moves to Q0. Similarly, when 0 is applied to the state Q0, then it moves to Q2. Q2, and the rest of the string is 1 0 1. The input 1 is applied to the state Q2, then it moves to Q3. And input 0 is applied to the state Q3, it moves to Q1, and the rest of the string is 1. When input 1 is applied to the state Q1 and it moves to Q0. So there is no string that is the empty string. And we get Q0, which is by property 1. What is property 1? Del R Q gamma lambda is equals to Q. So the part of the value part is Q0 to 1 is applied, moves to Q1, and 1 is plane moves to Q0, and 0 is plane moves to Q2. Similarly, 1, 0 moves to Q1, and 1 is applied Q0. And we will continue in the next class.